Hello everyone, so in this video I'll be talking about the solar cell and basically how the solar cell operates. So a solar cell is nothing but a p-n junction diode. It's basically a p-n junction diode. So let's say you have a semiconductor, and this semiconductor is a p-n junction, which means one part of it is p-type semiconductor and the other part is basically n-type semiconductor. And when you join this together, it becomes a p-n junction. So this is your p-n junction. Now in a p-type semiconductor, the semiconductor is basically doped with group 3 elements like boron, aluminium and gallium, right? And here basically your majority charge carrier is holes. Okay. And in n-type semiconductor, it's basically doping of silicon or any other semiconductor with group 5 elements like nitrogen, phosphorus, astatine, like nitrogen, phosphorus, right? Astatine. So when you dope this group 5 this semiconductor with the group 5 elements, the majority charge carrier becomes electrons. Hence the name is what? N-type, right? Negative. And here is p-type, which means it's positive. So holes are basically positively charged particles, right? So as you can see, you have the majority charge carriers, which are holes, and here the majority charge carrier are electrons. Now whenever you have this p-n junction, what happens is this hole, the neighboring hole and electrons, they'll try to recombine. They'll try to join together and neutralize each other, right? So what happens is when they recombine, they vanish. So this hole and this electron, they'll vanish. So when it vanishes, the part of this negatively charged, the n-type semiconductor, it becomes positively charged, right? And this part will become basically negatively charged, right? It's because since more of the electrons are going away, it becomes positively charged, right? Since this part vanished. And here, since most of the holes are moving to this direction, it becomes negatively charged, right? So as a result, what you have here is it creates an internal electric field, right? From positive to negative, and we call this the depletion region. Okay, depletion region. And since we have an electric field, what you will also have is basically a potential. So we call that potential barrier. So in order to pass electrons through this, you need to exceed that potential barrier. For example, for silicon, it's basically 0.7 volt. Alright, so here is the depletion region, and this is basically your p-n junction diode, which is like this, right? So this is your p-type and this is your n-type. Now what happens is, what sets it apart from a p-n junction and the solar cell is that in a solar cell you are shining light, right? You're shining here photons of light on this p-n junction diode. And we know from the band theory, you have the valence band and the conduction band. So right now in this depletion region, your valence band is what? Completely full. There's no, it's basically full. And here in the conduction band, it's empty, right? Because there is no conduction here. Now when you shine light on this p-n junction diode, these electrons from the valence band, they'll gain energy, right? And when it exceeds that potential barrier of, let's say, 0.7 volt, it will try to go to the conduction band here, right? So as a result, what happens is, as the electron is moving here, it creates a electron hole pair. So you're going to have in this depletion region an electron and a hole pair, electron and a hole pair, right? So a lot of electron and hole pairs are going to be generated here. The same goes for this n-type and the p-type as well. But the problem here is, in these regions of p-type and n-type, these electron and hole pairs are going to recombine. Okay, they're going to recombine, and so for a certain amount of period they're going to have that negative, that electron and a hole. But since there's no internal field like in this depletion region, they're going to be just recombining again after a few moment of time. But if you look at this potential barrier, once you have that electron hole pairs, the internal field, what will it do? Here it will attract these electrons on this direction, right? Since it's positively charged, so the electrons will move in this direction, right? And what happens to the holes? The holes are going to move in this direction, the opposite direction. So as a result, your electrons are going to accumulate on these sides. More and more electrons will be accumulating, right? And more holes will be accumulating on this p-type, right? As a result, you're going to have an external field where you have a lot of electrons here and a lot of holes here, right? So this is going to create an external field within the p-n junction due to this shining of this light. Now what we do in a solar cell is, we have this metallic plate. We use a metallic plate so that electrons can now flow through the external circuit and move through it. So we can complete the circuit now. So let's say now I place a lamp here. Now this lamp will light up because it will try to, the electrons will try to move to the higher potential. It will try to move through this external circuit now, right, and go to these holes. And that's how basically the solar cell operates. Thank you.